In this section, we look at definite integrals where one or more boundaries of integration is improper. So we call these types of integrals improper integrals. Now, improper integrals are going to mean one of two things. Either, as you see down here in our first example, either an endpoint of integration is infinite, or we're going to have some sort of a discontinuity either at an endpoint of integration or in between the endpoints of integration. Okay, so we'll talk about that in a little bit. But I want to first start out by looking at this example here that we're trying to compute the integral from 1 to infinity of 1 over x squared dx. Okay, so this integral is improper at x equals infinity because we cannot claim that 1 over x squared is continuous on 1 to infinity, okay, since infinity is not a proper included endpoint for such an interval. Okay, instead we consider the integral from 1 to b of 1 over x squared dx. So let's look at that first. So I left a little space here because I'm going to add a little something there. If we let b be some random constant greater than 1 here, in which we can easily see that from 1 to b, the area beneath the curve, 1 over x squared, beneath the curve and the x-axis is finite. Okay, so if we evaluate the integral from 1 to b of 1 over x squared dx, and then we send b out to infinity, and they use beta in this diagram here, but I use b. We send b to infinity, and we just then would take the limit as b approaches infinity of this, whatever we get when we evaluate the integral from 1 to b. So let's go ahead and evaluate the integral from 1 to b. Okay, so it's as simple as that. I'm just going to kind of sneak up on, send b out here and then sneak up on either a finite number or maybe we don't get a finite number. But nevertheless, you should be realizing here that what we're actually doing here is we're trying to figure out excuse me, we're trying to figure out if there's actually a finite area, if there's a number that represents the area between the curve and the x-axis, even though that region is infinite. So it's kind of an interesting concept here. We're trying to find a finite area for an infinite region. And you've done this before, though. I might remind you that the sum of an infinite series would be the first term over 1 minus the common ratio. And so you've already done these kinds of things. You've already added up an infinite number of things and gotten a finite number. So we're just basically trying to do the same thing here. All right, well, let's continue to just write the limit notation. This is probably going to be your biggest headache, is continuing to write that, because I want you to write that every time. If we look at this definite integral from 1 to b of 1 over x squared dx, I like to write it in terms of x to the negative 2. That reminds me, or it actually makes it easier for me to find the antiderivative. Okay, so again, limit as b goes to infinity. Now, what the antiderivative of x to the negative 2 would be x to the negative 2 plus 1, or x to the negative 1, over that number, negative 1. And we're going to evaluate that from 1 to b. Okay? Yeah, it's kind of a pain to keep writing that. But I'm going to clean this up just a little bit. Negative, or x to the negative 1 is 1 over x. Over negative 1 would just be negative 1 over x. Okay? And then again, that's from 1 to b. And limit as b goes to infinity. Now, when we replace x with b, we get negative 1 over b. Okay? Minus, so we have this antiderivative evaluated at the upper limit minus this antiderivative evaluated at the lower limit. Okay? So cleaning that up one last time, we can see that we get negative 1 over b minus minus 1 would be plus 1. Well, we also this is a great section because we get to practice our limits. We know that when the denominator of a fraction gets really, really big, then that fraction's value goes to 0. You know, as long as the numerator is a constant and the denominator is getting very large, then this fraction actually approaches 0, so we replace it with 0. and we just get a limit of 1. Okay, so from this we conclude that we can say, therefore, the integral from 1 to infinity of 1 over x squared dx is